Contestar. Okay. Okay, so good morning, everyone. Thanks for coming. It is my pleasure to introduce you to Michael Heap and Alexandra Kushnir. Michael Heap is expert in rock mechanics, specialized in rock mechanics in volcanic rocks and hydrothermal alteration of volcanic rocks. He comes from the University of Strasbourg. And Alexandra Kushnir, you want to come first? So I introduce you at the same time. Alexandra Kushnir, she is from the EPFL laboratory in Lausanne, and she is expert in rock physics. Okay, so they're going to give us 2 talks. There was like 20 minutes each.
Yeah, I'm just going to set a
okay.
stopwatch thing.
And yeah, thank you so much for coming and enjoy the talk. You start now, Matt?
Yeah. So thank you for coming to listen. I'm going to give a little bit of a whirlwind tour of some of the work that I've been doing in the past years, which is very much, as Adelina mentioned, combining rock deformation experiments. So my training is in a laboratory, breaking rocks and measuring their strength, measuring the strain at which they fail, and how those measurements can become relevant to inform on volcanic hazards. How can it help volcanic monitoring and understanding the hazard potential of volcanoes? So this is why I set the clock, because I'm already talking too much. So I'd like to start. I'm going to give you a bit of introduction into alteration, which will help Alex as well, because Alex will also talk about alteration. The first slide, alteration is ubiquitous at volcanoes, apart from all the volcanoes I visited yesterday. So here's a few pictures of me at some very nasty volcanoes. Fakari volcano in New Zealand on this side, and La Soufrière de Guadeloupe, which is a place I've done a lot of work on in recent years. And so very often when you go to a volcano, you see alteration, and alteration is linked to a variety of hazards. When you look at the deposits of debris avalanche deposits, so this is La Soufrière de Guadeloupe, the dome here, this is debris avalanche deposit. And what you can see even from this aerial photograph is the rocks are white, they are yellow, they are altered. And so without any more evidence than that, you might expect that there's some link between what happened and the nature of the rocks. So that's in terms of mass wasting events, but also in terms of erratic phreatic and phreatomagmatic eruptions. Volcanoes with very well hydrothermal systems tend to have this interaction between the hydrothermal system and the magma, which creates all sorts of very hazardous explosions. So this is a little video and a photograph from Poas volcano in Costa Rica, where we can see these sorts of hazards. So, however, this link is generally well understood, but it's more of a as I mentioned with the landslides, more of a causation type link. We lack measurements, we lack models to really understand how alteration is affecting things and how to best prepare ourselves for the inevitable consequences of this activity. What's really challenging and why I guess we don't know a lot about alteration and hazards is that for a lot of our volcanic activity, we have telltale precursors, we have earthquakes, we have ground deformation, all these things that we can monitor and we can measure. But very often, hydrothermal alteration is more like a ninja, and it is changing the properties of the rocks very slowly, very imperceptibly. We can't measure it, we can't listen to it. And events such as this, as emphasized recently around the world, in Japan, and also in the volcano I showed you before in Fakari, where there was a huge explosion and a lot of tourists were killed, unfortunately. These are hazards that we really struggle to predict for the aforementioned reasons. So I've been talking a lot about alteration. What am I talking about? It simply refers to a change. The process of altering or being altered. So that was taken from the dictionary. I was always told that you should not use the word you're defining in the definition, but there we go. So hydrothermal alteration, therefore, just means that a volcanic rock, which is fresh, it's juvenile, it's happy, is being changed by hot fluids, rock fluid interaction. This change can typically be, and if quite a few of you have a petrological flavor to your research, then this is not news to you, that these changes can be the dissolution of minerals, replacement of minerals, precipitation of minerals, and a various combination of the above. So I have a couple of examples. This is an SEM image in backscattered mode. This is a plagioclase that you can just make out. It's a very, very unhappy plagioclase. It's been altered by rock fluid interactions, and this has caused this pitting texture that you can see. What you can't see from the image necessarily is that there's a lot of replacement with clay minerals as well. So microscopically, this is what's happening to the rocks. So that was dissolution. If we look at precipitation, then this is another SEM image. This here, I'm outlining or trying to outline, is a pore, and it's been filled with hydrothermal precipitation. So it's been filled with cristobalite, which is a silica polymorph, and alunite, which is this mineral which is very common in acid sulfate alteration systems. So these have precipitated into the pore, also a type of alteration. What does it look like in the rocks? Well, it can be fantastically beautiful in a way, but the smell also very bad. So these are rocks from Merapi volcano. These are from Copaue in Argentina, and these ones are all from Costa Rica, so Rincon de la Vieja, Turrialba, and Poas. So all the colors of the rainbow, we can see that the alteration has really affected these rocks. In the one here, you can see that there's essentially native sulfur precipitated into the pores of the rocks. So that's what alteration is. I told you at the start that it changes the hazard potential of a volcano, but so why does it do that? And it's because the changes that I was just describing change the physical, mechanical, and hydraulic properties of volcanic rocks. And it's these properties of volcanic rocks which can influence how hazardous a volcano can be. For example, it doesn't take much of a stretch to understand that a decrease in the strength of a rock could reduce the stability of a slope. And that's one example that I'll discuss in the rest of the talk. The second example is that a decrease in permeability can be responsible, or is thought to be responsible, for this erratic explosivity that I mentioned. That if you stop the pressurized gases from escaping the system, then they will find a way, and they will find a way explosively, which is why people think that we have these sorts of phreatic explosions. So the alteration can change all these properties, which can change the hazard. So it's a diagram that I made to try and help. I'm not sure that it does. It's a little bit complicated. Quite a lot of arrows. We have a rock, a fresh rock here, and there's various ways that it can alter, as discussed before: dissolution, replacement, and precipitation. What I've tried to do is try to understand here what it's doing to the physical properties. So if you start to dissolve your rock, it makes sense that the porosity increases and that the strength would decrease. For example, if you precipitate, if you clog your rock full of mineral precipitates, then your porosity will decrease. And as a result, maybe your strength would increase. Because porosity is, for people like me, is very much a physical property which it doesn't dictate everything. But if you know the porosity of a rock, typically I could have a good guess at what the strength could be or what the permeability could be, because those factors, although confounding very often, are very much linked. So it's these two case studies that I'll talk about today. Dissolution type alteration, decreasing strength, how that affects the volcano. Precipitation type, let's just check the precipitation type alteration, how that affects permeability and therefore the hazard potential of the volcano. So for the example number 1, decrease in strength, we're going to go to La Soufrière de Guadeloupe and look at what alteration does to the rock. So what we have, this big graph here, is we have uniaxial compressive strength. So that's a very simple metric that we can measure in the lab. That's just the strength of the rock. We make a little cylinder of rock, we squash it in the lab until it breaks, and then the strength at which it breaks is the uniaxial compressive strength. And on the x-axis here, we have alteration. And that's defined by here and by me as just the percentage of secondary minerals in the rock. All the rocks went through X-ray diffraction, and everything that shouldn't be there was classed as an alteration mineral, and it's simply the percentage or the ratio of primary to secondary minerals. Okay, so each of these points on the graph is a different rock. So each dot is a single experimental sample, which we know the alteration of, and we crushed in the lab to find its strength. So if you ignore these two here, and there's good reason for ignoring them that I won't talk about right now, what you could see with the eye of faith is this kind of trend here, that as you're increasing the alteration up to 80%, which is the maximum that we saw, we're decreasing the strength of the rock from 120 megapascal down to 20 megapascal. So those numbers are not necessarily important, but as a percentage of strength reduction, that's quite a lot. So that's what alteration is doing to the strength of the rock. Why is it doing it? Well, we touched upon this just before. It's doing this because of these rock-fluid interactions, which are affecting the microstructure of the rock and therefore impacting the macroscopic physical properties of the rock. We're likely increasing porosity. We are dissolving minerals. There's lots of unhappy plagioclases. We're replacing primary volcanic materials such as glass, which is very strong, with secondary minerals such as clay, which are notoriously weak. And so the more altered you are, the weaker you are because of these processes. Okay, so then how does that influence the hazard potential of a volcano? Okay, this is complicated. I'll walk you through. So we did numerical modeling to try to understand this. It's based on data from La Soufrière de Guadeloupe. What we have are 4 different scenarios, okay? So this is the present day scenario where this is a 2D slice of the volcano. And in the present day scenario, there's a very highly altered zone indicated by this dark gray banana, which is in the shape of a banana. And a lot of the flank stability is dictated by this alteration zone. Okay, so that's present day. That was illuminated to us by electricity resistivity tomography. Okay, so we're going to go back in time and forward in time. If we go back in time and we remove this highly altered zone, then maybe we have a volcano which is homogeneously altered, but it's only moderately altered if you check out the little scale here. Further back in time, having been to the volcano, I can't imagine a situation where it was not altered, but this is the volcano if it was not altered at all. And then this is forward in time, which is also sad times, where the southern flank of the volcano, this is the south side, is now completely altered. Okay, so these are the 4 scenarios. Let's only have a look at these ones here. Just ignore the ones in the middle. And so the color on the surface relates to the velocity, millimeters per year, where if it's blue, nothing much is happening, and if it's yellow, there's quite a lot happening relatively. Ignore the numbers, it's just a model. And inside the volcano, white means that there's nothing happening, and yellow means that there's lots happening. So what we can see is our present day scenario is that there's a lot of movement on the flank of the volcano here. There's some high strain rate zones inside, which are related to this banana-shaped alteration here. If we go back in time and we unalter the volcano, we see that nothing much is happening. So we could maybe conclude here that some of the deformation that we see is a result, the highly mobile southern flank of the volcano is a result of some of these alteration zones that are prevalent in the volcano. If we go forward in time and we make the whole flank altered, then as you can see here, there's a lot of movement. And so what you could conclude here is that alteration is an increase in alteration will increase the rate at which the flank is moving and will increase the volcanic hazard. An important point that I didn't mention is that these numerical models are completely populated by laboratory measurements, which have either not been upscaled or have been upscaled. So we used all the information from the lab to go into the model. And although there's been a lot of work in this direction, there wasn't so much in the way of laboratory people talking to the geologists, talking to the geochemists, talking to the modelers in order to create something like this. And so hydrothermal alteration is super cool because you have to have lots of friends with different skills in order to understand what's going on, which is where I like to do my science. Okay, that was strength. Okay, so alteration can decrease strength, change the slope stability of a volcano. I also mentioned alteration. So what's that doing? I have two graphs to show you here. We have permeability as a function of porosity, and again, permeability as a function of porosity from rocks from different volcanoes. So this is a volcano in Lassen National Park in America, and this is Merapi in Indonesia. Again, each point is a different cylindrical sample that's been measured in the laboratory. And what these arrows show, to make it easy to understand, because there's quite a lot going on, what these arrows show is the direction of alteration, if you like, in terms of which sample is more altered than which other sample. So if we stay here, which is the easier graph to understand, then the black ones and the gray ones are not very altered at all. These white triangles are reasonably altered, and the black triangles are very altered, which you can see in the picture as the rock changes from gray to yellow. But what we see here is that the permeability changes from 10 to the minus 14, which is quite high, down to 10 to the minus 17, 18. So altering these rocks has caused a huge decrease in the permeability. And the same is true, although I won't explain it because it's a bit more complicated here. The same is true from rocks from Merapi volcano in Indonesia. So here, the alteration is decreasing the permeability. And so why? So again, we can go on the SEM. So these are all backscattered SEM images. And what we see are pores and cracks. And for me, the pores and cracks are the highways that fluids use to move through a rock. And so these highways in these rocks are full of mineral precipitation, which is stopping the fluids from moving. So we have pores in this rock here, are full of kaolinite. They're also full of cristobalite. There's some cristobalite here. Has another sample from the same volcano. This crack here, which would normally be a very effective channel for fluids to move through, is completely clogged up. And over here for the Merapi samples, we have the same story. We have pores that are covered in mineral precipitates and cracks that are full up. And so this is the reason why the permeability is decreasing. Okay, so if alteration can decrease permeability, then we need to understand how that can influence the hazard potential of a volcano. Okay, so here's some modeling from using COMSOL. So it's 2D. Hopefully you can spot that this is a little volcano at the top here. And all we've done here is assign different permeabilities to the top of the volcano here. This is designed here to represent the dome of a volcano. And so the conduit, which you can just about see, is quite permeable. The host rock here is reasonably permeable, and that's fixed from each of these 3 modeling runs. The only thing we change is the permeability of the hat of the volcano, of the dome. And so we change that from 10 to the minus 11, 10 to the minus 12, to 10 to the minus 13. So this is, long story short, this is informed again by the laboratory measurements that I just showed you. What you can see in the different colors, that these lovely Bordeaux colors are low overpressure, low bubble pressure, and yellow and white are very high pressure. So what we can see is as we decrease the permeability, we're generating these overpressures, these poor overpressures in the top of the conduit here, just below the dome, as we decrease the permeability. So the alteration is decreasing permeability, and it's increasing the pressure underneath our volcano, which is never good. It's never good to have pressure in your volcano. And so I didn't give you the values, but the overpressures predicted by the model are sufficient to fragment rock and magma based on some simple micromechanical models of fragmentation. So in this case, the alteration has increased the hazard potential by reducing permeability and increasing the likelihood of some sort of phreatic or phreomagmatic eruption. There's a little cartoon, because everyone loves cartoons. So we have 3 stages. We have an outgassing stage where the gases can escape and everyone's happy. And then we have some alteration, which clogs the system. We have our fractures are filled with mineral precipitates, so then the fluids can't get out. And then eventually we have an explosion, which is the result of this pressurized gas trying to escape. So in summary, alteration is ubiquitous of volcanoes, apart from the ones that I saw yesterday. It changes the physical, mechanical properties of the rocks. And we've seen through combining lab measurements and modeling, we've seen that if you believe all the numerous assumptions that are buried into this model, those models, that they can influence the hazard potential of a volcano, which includes mass wasting, landslides here, partial flank collapse, and this sort of unwanted erratic explosive behavior. So as I mentioned earlier, alteration is a challenging topic because of the multidisciplinary nature of everything. I think we need geophysicists who are trying to monitor the signals. We need people like me. We need people that understand clay and alteration. We need all these people combined to try to understand how it's happening. And at the moment, we don't have a telltale signal. We can't say, oh, this is when this hydrothermal eruption will happen, because we don't yet know enough. And as a result, alteration is not part of routine volcanic monitoring. And so there's some work to do. And like a shameless plug alert, we won some money through the European Research Council to do exactly what I've just been describing, this multidisciplinary approach. Sorry for the corporate style graphics. So there's a team of 4 of us from remote sensing for geochemistry. There's me in the lab, rock physics to modeling, which are all focused on synergistically combining our strengths to understand volcanic hazards and how they influence eruptions. So we're going to do this through various work packages, which are pretty obvious. Where is the alteration? Like, how does it change the rocks, and what are the hazard implications? So what I've just been describing. And so in the next 6 years, we plan to try to push the boundary and understand what's going on. Thank you very much.
Thank you so much, Mike. Should we go to your talk? And we can there is the questions for later, Mike. Is this fine with you?
Yes, perfect.
Yeah, we can have a discussion later. Yeah.
Okay, I'm gonna come down to your level because it's too it's too bright up there. Hope you guys don't mind if I move around a bit. Is it okay? That's perfect, thank you. Okay, hi everyone. Thank you so much for having us. So I'm Alex. I'm very. Oh, okay. Okay, I'll keep talking. Hello, people on YouTube. Thank you very much for having us. We're really quite excited to be here. And Mike's given a really nice overview about why, as rock physicists, rock mechanics people, we care about alteration. And so what I want to do is I'm probably only going to talk for about 15 minutes or so. I want to tell you what my group is doing. So I'm at EPFL, which is in Lausanne. It's the Polytechnical Institute of Lausanne. And I have my own group called the Rock Physics and Geofluids Laboratory. And what we're doing is we are running alteration experiments to see how alteration changes the physical properties of rocks. So the research we're starting with right now, it starts with this SEM picture. So this is a basaltic andesite from Merapi. The rock was erupted in 2010 during its paroxysmal eruption. And I first saw this rock during my PhD. And what I love about this rock, so I am not a petrologist. So to the petrologists in the room, I am sorry. I would love to talk to you afterwards. I do rock physics. I really care about permeability, okay? So when I look at SEMs, I actually look at the black space in SEMs. I look at the void space. And it's because it's the void space where all your gases are flowing through, where all your fluids are flowing through. So your void space is controlling your permeability. And what I love about this is this cristobalite in the middle. I'd never seen it before. I didn't know what it was. I thought it looked really cool. But what's really interesting about it is pore filling. Okay, so what it's going to do is it's going to be blocking up some of the pore space available to fluid flow. And presumably, this has a result on the permeability of that rock. So I first saw it in these rocks from Merapi. During my PhD, I sampled those rocks from PDC deposits, and I found kind of 3 different types of rocks. Initially, we called them, well, initially and always, we've called them juvenile. So rocks that we think originated very much from the magma that was erupted during the 2010 eruption, and then non-juvenile rocks on your right-hand side. These are rocks that we think were remobilized by the dome during the eruption from the previous dome, okay? So these non-juvenile rocks, they date back to about 2006. The reason that I think that that is important is that means that they cooked for a bit at the top of the volcano, so at low pressure and at low temperature. Now remember, I care about permeability. So here is a plot that is a little bit familiar to you guys now. It is going to be the permeability as a function of connected porosity of rocks from Merapi. You've seen some of these data points already. They are some of the rocks that Mike has already shown you in that previous graph. I've already divided them into the 3 groups. So I have my pumices here in the white symbols. I have my blocky juvenile material in the red. And then I have these non-juvenile kind of light gray rocks in the yellow. And what we see is that these pumiceous samples, these really vesiculated samples, they have high connected porosity and relatively high permeabilities. And that makes sense, right? Like if you look at the SEM image here, we've got lots of pore space. We've got lots of vesicle space. As we look at these more dense blocks, we see that they span a wider range of connected porosity and permeability. The reason for this is because when we're up at this end of that rock sample suite, we are very vesicle dominated. As we move down this trend, microcracks start to play a much more defining role in the permeability. So remember, Mike talked about how those microcracks are like the superhighways through rocks. As we go down this trend, our rocks are getting more microcracks in it. The microcracks are dominating the permeability, but we're losing those vesicles, right? So the porosity of those rocks is going down. And finally, we have these non-juvenile rocks. So these are these really dense light gray rocks that we see in hand sample. And they're really interesting because they're our lowest permeability rocks, they're our lowest porosity rocks, but they have a really interesting microstructure. They have these kind of microporous spaces within them. And I'm going to talk a little bit more about those, but what that is it's actually just the empty space between microlites. So where you would have initially had volcanic glass, there's now no longer volcanic glass in a lot of these materials. What's wild about these samples, though, is when we start to look at their internal specific surface area. So SBET, that's the internal specific surface area of your rock. That is how much surface is available inside your rock and what is going to be interacting with fluids. So think of it as the walls, the surface area of the walls of your permeable channels. What we see in the juvenile material is they're all kind of within an order of magnitude, right? We're in these blocky materials, when we're lower down in these micro crack dominated microstructures, we have lower specific surface area. And then as we introduce vesicles, we have more specific surface area. And then obviously the pumices or these pumiceous samples have quite a bit of surface area, right? Because you've got the inside of those pores. What's really cool though, is what's happening in these low permeability, very dense rocks, is we have these enormous specific surface areas. They're quite a bit larger. And so remember, that's that microporous texture. So we have a lot of this tiny little porosity within the sample. It incorporates a lot of surface area, right? So it produces a lot of surface area, but that space, that porous space is not necessarily very efficient at flowing gas through it. So you have low permeabilities, even though you have a lot of pore space surface. What I noticed when I was looking at these rocks, and you're going to see in a moment that I am not by any stretch the first person to notice this, but I was in my PhD. I was a bit young, a bit naive. What you always see in these rocks is that this microporosity, so remember microlites without any interstitial glass around them, is always associated with pore filling cristobalite. And when I look at the non-juvenile materials from that eruption, so this is another larger scale SEM image of that, I see that wherever I have this microporous texture, I have loads and loads of cristobalite. So on your screen right now is cristobalite that's highlighted in yellow. So it's chock full of this secondary mineral. As I said, I'm not the first person to see this. This has been really well documented in the literature. Cristobalite is everywhere in these continental volcanoes. We see it at Colima, we see it at Kaiten, we see it at Ruapeu. And there are some microtextural characteristics that are really very commonly reported. The first being that we often see cristobalite. So here we've got two SEM images. Again, these are from Merapi, so these are from the samples that I took a look at that do provide kind of nice examples of these textures reported in the literature. On the left-hand side, we have something called feather textures. So this is cristobalite that is found between the microlites, right? So this is kind of a precursor to that microporosity that I was showing you earlier. These feather textures are interpreted in the literature as being devitrification textures. So you've got your volcanic glass that's between the microlites. That glass devitrifies and it crystallizes into cristobalite. The second texture that we always see is we see this pore filling cristobalite. So you see these euhedral cristobalites that start to grow into pore spaces. This is interpreted as vapor deposition. So this is interpreted as being the product of having silica-rich vapors flowing through the volcanic rock and depositing cristobalite. Importantly, these are post-emplacement features. Okay, so they're not from the magmatic melt, right? So cristobalite in these rocks, we don't think is crystallizing from a melt phase. We really think it's some sort of secondary mineralization. And so, to fit Mike's definition of alteration, we think it's alteration, okay? So something is happening to the rock that is then allowing for cristobalite to form. That cristobalite is changing the pore structure of that rock. And so the pore structure of that rock must therefore influence the permeability of that rock. So the formation of the hypothesis is the formation of cristobalite changes the permeability of volcanic rocks. What's weird about cristobalite, though, is we shouldn't see it in these systems. Okay, so you have a phase diagram of pure silica, silica and water, and haplogranite on the right-hand side of your screen. And what you can see is that cristobalite is a low pressure silica polymorph, but it's super high temperature. So we shouldn't really be seeing it below 1400 degrees Celsius, which none of our volcanic systems are seeing, especially once the rock's formed. Oh, where's my water bottle gone? Okay, so that means cristobalite is metastable in these systems. And we think it's metastable because of the presence of sodium, potassium, and aluminum. So cristobalite is not pure silica, and these mineralizing agents basically lower that stability field of cristobalite so that it can form. And these are typical elements that we see in volcanoes. So does cristobalite decrease rock permeability? Here are the rocks from Merapi. These are the ones that have cristobalite in them. We have permeability as a function of connected porosity. And as we go up this plot, we see that we have increasing cristobalite content, increasing microporous texture, increasing fracture density. Okay? So what this says is that permeability is just always increasing, right? With all those things that are changing, permeability is increasing. But remember that the cristobalite should be pore filling. So this is counterintuitive to what our hypothesis would be, right? We would say if we're reducing the pore space by precipitating cristobalite, then we should reduce permeability, right? There are a few reasons why this is a little bit disappointing, but also I think that we can explain this, is that these are natural materials, okay? So already my sample set, it's pretty small, so I can't say so much about that really statistically. But remember that I also have the microporous texture increasing up the plot, and critically, I have the fracture density increasing. And remember that those fractures are the superhighways. So the fractures and the cristobalite are fighting each other, presumably, in their response, in the permeability response of that rock. And remember that because these are natural materials, like my microstructure is recording a lot of history, right? So your rock starts in the mantle, it comes up through the crust, it changes composition, it exsolves its volatiles, so it creates bubbles. Those bubbles expand as we go up higher in the crust. They connect the outgases from the rock, the bubbles collapse, your magma's erupted, it runs down a hill, and it gets all fractured up. So what's happening is that the microstructure that I'm seeing in a natural rock, I can't actually really necessarily relate it to one single process, which means that I can't necessarily take any conclusion from this plot, right? Because I don't exactly know which process has been dominant when I've made this plot. So I'm at the point now where I think we have more questions than we have answers, right? And I'm going to kind of tell you what our groups, remember I said I wanted to tell you what our research is about. So I want to tell you a little bit what my group is doing, is starting to do within this space. So where do we go from here? Where do we go from this fundamental question that we have of, does cristobalite reduce the permeability of volcanic rock? What we want to understand is the physical and the chemical constraints on alteration processes in volcanoes. So what is the pressure and the temperature that you need for certain alteration? What are the chemical conditions, right? How many of those mineralizing agents, remember I said we have potassium, aluminum, sodium, how much of that do I need in order to make crystallite? What are the time scales of these alteration processes, right? If it's going to take me 10,000 years to do this, is that really something that matters on the human scale of eruptive processes that endanger towns, that endanger people? Or is this something that can happen in a couple months? You know, the time scale really matters for that hazard mitigation. And kind of the scientific thing that I'm really interested in is once we start altering these rocks, what is the link between the geometric changes to that pore structure and the permeability of the rocks? So in order to do this, what we want to do is we want to run systematic experiments. We want to run systematic studies that assess the role of fluid rock interactions on permeability under volcanic processes. And that brings me to the work that we're doing now at EPFL. So I am hired for 5 years as a research and teaching associate. I've got my own group with a couple of students who you'll see a picture of in a moment. And we're hired under a career framework. So we're hired for 5 years, and the project is called Residue. So redistribution of silica and deposition under a volcanic edifice. And our fundamental question, our quite literally million-franc question is, does silica redistribution change the permeability of rocks under volcanic conditions? So here's the team. You've got myself, you've got Cindy Mikaelian, and you've got Andrea Mazzeo, who are the PhD students in my group. And behind us, you have what our lab space looked like a year ago. Okay, so we're experimentalists, right? It took us ages to get our experimental equipment in. I'm going to show you some of our equipment that's now been delivered. But this is what we started off with. We started off with a little corner in a pre-existing lab at EPFL. And what we're trying to do together is we're trying to take a really systematic approach at alteration. So remember I said that that natural material, there's all that overprinting of microstructure, and so it's really hard to untangle what's going on. So what we're going to start doing is we're going to alter analog glass bead or natural sandstones, clean sandstones, to take a look at what alteration does to geometry, so the geometry of pore spaces. The reason we like that is it's a simple composition and it's a simple microstructure. Next up, we're going to look at synthetic sintered glasses. So again, something that we can synthesize in the lab, something that has a relatively simple microstructure, but with more complex geochemistry, so we can control for those mineralizing agents within the glass itself, right? So if we can try and see how much sodium, how much potassium, how much aluminum we need to add to a system in order to make some of these silica polymorphs. And then finally, we do want to come back to the natural volcanic rocks. So we want to see if we can replicate what we see in nature, if we can replicate that in the lab under controlled conditions. So we've divided this into the 3 different materials, but also the 3 different goals. So Andrea is working on how silica alteration modifies the permeability of geometrically well-constrained systems. So a system of very nicely well-constrained spheres, how do we fill up the pore space or dissolve the spheres in order to change permeability, and how fast that happens? What Cindy's working on is she's working on those mineralizing agents. So how do the complex volcanic fluid and glass chemistries promote silica alteration? And then there's me. I get to do the fun natural rock stuff. So once we kind of get these first 2 work packages ready and well constrained, then can we start playing with natural rocks and start to replicate what we see? So to do this, what we've done is we've designed a high temperature reactive permeameter. So this is a piece of equipment, I'll show you a picture of it in a moment, that we designed with top industry. It is an externally heated permeameter that allows us to go up to 500 degrees Celsius. So we're looking at kind of upper edifice temperatures. We're looking at dome temperatures in this material, in this system. What it lets us do is it lets us go up to 100 MPa in confining pressure, which is about 5 kilometers depth, Right now, we're operating at about 20 to 40 MPa, just as we're kind of characterizing the machine and getting everything going. And critically, what this system lets us do is the system is equipped with a flow-through system, a flow-through pore fluid system that allows us to pump fluid through our samples at high temperature and at high pressure, and allow us to monitor permeability evolution over time as we are reacting those rocks within the machine. For this system, we can go up to about 20 MPa in pore fluid pressure, and we have a mixing vessel. So we have a mixing vessel that allows us to precondition our fluids before that fluid reaches the sample. So hopefully, at least at the moment at which we hit the sample, we're in some sort of equilibrium before we then place everything out of equilibrium. Right now, we've just finished up some calibrations. We can measure up to about 10 to the minus 12 meters squared. So that's a Darcy in permeability. So we can start with some really permeable materials and then try to reduce their permeability over time with alteration. And the other nice thing about this machine is that it's made of a material that allows us to use reactive fluids. So high pH and low pH fluids, so that we can really start etching away or precipitating material and using the pH of fluids to do that. So where are we at? Harold has arrived. So our high temperature permeameter is called Harold. This is before Harold was fully installed, so he's still got some bubble wrap on him. He's now fully installed, fully enclosed. He's got a great fume hood on him because as we start dealing with acids, don't really know what's going to come out of the machine. And up till now, what Andrea's done is he's finished off the calibration of that machine. We know the permeabilities that we're dealing with. So the maximum permeability that he can measure, including all the spacers and basically the permeability of the machine itself, is 7 times 10 to the minus 13 meters squared, which is pretty close to the target we wanted. So we're quite happy with that. And he's in the process of looking into the fluid chemistry contamination due to the machine itself. So as we're flowing a pore fluid through all the pipes, that pore fluid is going to react with the pipes. So what we need to do is we need to know how, so that then we can remove that signal from any data that we might gather. The next steps, Andrea currently is at a workshop. When he gets back next week, he is going to alter a sample with calcite. This is the first time I've mentioned calcite, right? The reason for that is because we don't really know where everything is going to precipitate, right? We want it to precipitate in the sample, but it's going to precipitate in the pipe somewhere. We need to understand how that machine is going to react to the various types of experiments that we can do. And for that, we use calcite. We use calcite because it's really easy to clean. We can pump vinegar through the system afterwards, and we're great. As soon as we start playing with silica, we're going to start having a few more problems. So we're starting with calcite alteration, and then the next step after that is really to then start focusing on what silica alteration is doing to the geometry of glass bead samples. As for the role of mineralizing agents, so Cindy's been with me a little bit longer. She's been with me about 6 months longer than Andrea, so she's a bit further along experimentally. What she's been doing is she's been synthesizing and altering volcanic key glasses. So what that means is that she is making synthetic glasses of approximate volcanic compositions, of rhyolitic compositions, and trying to alter them under batch systems, so under closed systems to try and constrain the chemistry of alteration. So here we have some pictures of the glass synthesis in which she mixes oxide powders, melts them, grinds them, remelts them, grinds them, remelts them to get a homogeneous starting glass that is non-crystalline. What she then does with that glass, so really an amorphous material, is she then places it in these little autoclaves. So these are little stainless steel autoclaves that have an inner cup of Teflon in them so that liquid and solid doesn't react with the steel itself. And she's using small amounts of glass. Sorry, there we go. She's using small amounts of glass with various fluids up to pressures of only 1.5 MPa, so relatively low pressure, but up to high temperature, so 220 degrees Celsius, to see how her glass is reacting with vapor, right? So remember earlier I said that the vapor deposition of cristobalite is one of the hypotheses for its formation. What she's interested in seeing is how does glass interact with vapor, and does that cause any sort of crystallization? To date, she's been running a few batch experiments. So she's using 2 different glass compositions that are varying in sodium and potassium content. They all have aluminum in them and they all have silica in them. And she's using high pH and low pH fluids to see how they're reacting. Each one of these little autoclaves is one experiment, and each one of them is a time step. So what she's doing is she's putting a bunch of autoclaves in the oven on day 1, and every week she's taking out one of the high pH, one of the low pH, and one of the either glasses to see over time how that's changing. So the analysis of that is in progress at this time. So what I've outlined for you guys today is kind of our experimental approach on how we're trying to learn more about how alteration changes the petrophysical properties of rocks, specifically permeability. And for us, that goes beyond volcanology. So we're working on volcanology right now, but ultimately we're hoping that everything that we're learning right now, we can apply to various different Earth systems, right? So anything that we're doing now, we're hoping is relevant to geothermal energy. We're hoping it's relevant to perhaps more complex ore systems that we can then modify our experimental techniques to analyze and to study. And fundamentally, the questions that we want to answer are, where should we expect alteration within a geological system? How quickly does alteration occur? So what's the speed of these processes under relevant geological conditions? And also, how do these processes promote or hinder permeability, right? We're always coming back to that petrophysical question of how does alteration change fluid flow in the crust? So with that, I'd like to thank you very much for your attention. I think Mike and I are both very, very open to questions. And again, thank you very much for having us today. We've had a really great last 2 days in Barcelona, and we would really love to come back. So thanks.
Thank you very much. Any questions? Yep. Which one? Or in general?
Does Mike want to come up?
Mike, you may go closer to the microphone.
Sorry.
Share
You got to wake up.
I'm not sure the other ones are working.
That's okay. We can share. Mike.
I'm interested in knowing exactly how are you going to, or how would you factor in this competition between alteration and microfracturing, because as Mike was pointing out, there is this alteration that is clogging the pathways, but there are other new pathways coming in because the build-up pressure is. So how do you incorporate that in your models? How do you incorporate that dynamic part where, you know, sorry.
Okay, so I'll start, but then I'm going to pass it over to Mike. My very simple, and I'm very sorry, disappointing answer is I'm not. So because with the experiments that we're trying to run is we're really trying to isolate process. And the first process I want to see is that porosity reducing process. And so none of the work that we're currently doing is going to be looking at the deformation of that material. Now, down the line, that is something I would love to do. And that is something that I think is really interesting to then see how that alteration allows for changes in deformation behavior. But that is not something that we are currently doing at EPFL, but I think Mike has some pretty interesting things to say about that within Rod and Rock.
No pressure. Yeah, I think you just given me an idea for a paper. So for the permeability model that I showed from the Merapi data, what we did that I didn't show is that we had drone data, and so we mapped out fractures with the drones. And so we gave those values of permeability, and then we kind of offset it in a way that you described by progressively filling it. What we don't have is the the time aspect that you implied in your question. So I guess what that would require is that we understand rates of alteration, which is what we don't quite understand at the moment, and rates of fracturing. I guess you could do both with remote sensing. If every month you droned an area, for example, you counted the cracks, not necessarily the micro cracks, but cracks on different scales, and you monitored how the alteration was progressing as well, then maybe you could combine those ideas together.
But I think you could also try, like, being a rock mechanic person, maybe this could also be kind of simulated in within a press, like trying to or
Sure.
I don't know, I'm just
So that as
thinking out loud.
part of the ERC, a large part of my budget is going to go to a machine that would be able to do that. And so it'd be a triaxial deformation machine, so we can deform rock, but it has a high pore fluid capacity, such that we can flow acid through the rock while we're deforming, and while we're measuring things like permeability, while we're measuring things like ultrasonic or elastic wave velocities as well. I'm trying to speak to more people that are active in the monitoring of volcanoes to see what sort of information they want as well, because I can hide in the basement as long as I want, measuring the little things that I think are important. And so, yeah, the machine that I'm going to buy should hopefully be in Strasbourg at the end of next year, and that can maybe tackle. So you could be precipitating whilst you're opening cracks through deformation as well. It sounds like a extremely complicated experiment, but very interesting.
Thank you.
Thanks.
Hello. Thank you very much for the presentations. They were great. And I have a question to Mike as well, because I wonder how in your rock physics model, at the end, the seismic velocity changes, because I guess the decrease in porosity will lower the velocity, but also you replace some minerals with weaker minerals that will change the bulk modulus, probably decrease, and therefore the seismic velocity. So I wonder how at the end, the seismic velocity is expected to change.
Yeah, so there's like a problem that's hiding in all of this. So I measured the P wave velocity of the rocks that I showed, and it shows that as you increase alteration, you decrease elastic wave velocities. So that might be useful. One of the aforementioned geophysicists, Corentin Colderan, who's in Brussels at the moment, he had a Nature Communication paper very recently about how maybe you can spot alteration by increases in P wave velocity or increases in elastic wave velocity associated with mineral precipitation. So in the volcano, you've got processes that are acting to decrease the elastic wave velocities and processes that are acting to increase it. And so I think the next problem is to try to get a 3D model of a volcano where maybe you have reaction rates, you have pressures, you have temperatures, and you try to understand where in the volcano you would have precipitation and where you would have dissolving. Because if you dissolve something, it has to end up somewhere. I guess I'm not a geochemitrist, or however I try to say it in the talk. As you're decreasing temperature, or you increase fluid, like the cargo in the fluid, that you're more likely to precipitate things. So and so, yeah, I guess I'm moving off topic. If understanding it in the lab might well be easy. I think if you have dissolution, that you're going to decrease. If you have precipitation, you're going to increase. Using that in a larger scale to look at monitoring might well be very difficult. It might be a bit like some of the data I've seen for radon monitoring, where sometimes you have positive and negative anomalies, and both ended up in an eruption, and I'm not sure why. So I think there's a level of understanding that I'm not sure that we have at the moment, but this is kind of where we're all working to, and we need all the friends to be able to do it.
Okay, thank you very much.
Just wanted that, this is something that she mentioned, that maybe measuring actually the VP-VS ratio would help, because if you're precipitating and you're clogging porosity or permeability, then you don't have fluids you have less fluid for so you have more passage for the VS waves, and therefore that would increase. Yeah, well, you know what I mean.
I understand. Yeah, so I think so. This is the sort of feedback that's really useful. Typically, I don't talk about S waves because they're more difficult to spot in the lab, or they're more difficult to pick the arrival time. But in the new system, I'd quite like to implement this and have P and S wave transducers, because a lot of people, I'm missing a trick. Like S waves are more difficult to quantify, or the velocity is more difficult to quantify. But I think the extra gain is massive, because a lot of people are interested in these sorts of things. So I will do this.
Here I go.
Sorry, I was just going to follow up with that, is that there's also the question of like electrical resistivity, right? So if we can monitor how those other petrophysical parameters change during alteration, then that actually makes it a little bit more relevant to the large scale, like geophysics that can be done. One thing is that in the lab, sometimes that's actually really difficult to technically implement. And so sometimes that's a cost thing, and sometimes that's actually like a technological thing. Things are really moving in that direction, and I think that there are a lot of boundaries being pushed in that. But I know when we were designing Herald, we wanted to put in like piezoelectric sensors to measure VP and VS, but we're operating at 500 degrees Celsius, right? So finding stuff that fits, finding stuff that isn't going to deteriorate with temperature, designing waveguides to be able to measure at cold temperatures what's happening at hot. It is very possible. One thing I'll say, it's quite expensive. And so with Herald, we did have to reduce our sample sizes because of cost constraints. But moving forward, this is something I think that we're all really excited about, is that it's like Mike said, having that sort of feedback is what are the geophysical parameters that people need. That's something that over time we can incorporate into machines. And so that's kind of like a really fun frontier for us, technically speaking.
Okay. Well, here I would like just to point out, just because it will be very interesting to have some studies about the velocity for S waves, because, well, I have been working in Iceland for several years in geothermal areas, and then I saw a very high correlation between the velocity for S waves and the resistivity and the mineral alteration in the area. But then to try to monitor something when you have, for instance, gas accumulation, it changes everything. So it dominates completely the rock physics model that you employ. But it would be very interesting to have some measurements of the S waves, because there are not many papers doing that. So in the experiment in the field, I have observed this correlation, but then in theory or in the lab, there are not many experiments combining these two variables, and it would be exciting.
Yeah, I already broke the rock, sir. That's what Corentin said to me. I showed him some data, and he's like, "Where's the S wave?" And I was like, "Oh."
So thank you for your talk. I'm sorry I arrived a bit late, so I didn't see the beginning, but I'm working on, I'm a geophysicist, more or less, and I'm working with induced polarization. So I was very interested about that, because alteration and fluid circulations are very interesting for this. So I don't have a clear question in my mind, but I'm very interested in talking about this with you, because
Yeah, 2 weeks ago we were at the top of La Soufrière in Guadeloupe, and we were doing IP. We were doing ERT and IP at the same time, and so we have time-lapse electrical resistivity tomography to look at how the hydrothermal system is changing and evolving in 3D. And so we spent 10 to 15 days doing a lot different lines, and more. And we did it 2 years ago, and we've just done it like 2 weeks ago. And 2 weeks ago was the first time that we did some IP as well. I'm not sure how good the data are, because we couldn't stay up there very long. and so we could only be measuring the chargeability up to about an hour or so, because it was dangerous, and also because it's was raining very heavily. Yeah. But I think that these sorts of methods are probably the best in terms of geophysics to look at how alteration is changing. And this is kind of shown in our data. Although some of it is really scary, and there's probably huge gas pockets underneath the dome where we were having our lunch, because we have these really super low super low conductivity, super high resistivity like packets, blocks. And so yeah, I think that's really cool.
Yeah, it is, because also I'm starting to work with industrialization since 2 years, and so we have models to interpret the temperature of the signals we measure. And so it's interesting because for now we only have models until 250 degrees approximately. So maybe making this, well, developing more models for high temperature, it would be very interesting to do some modeling also.
It's something that I'd really like to do in the lab, a bit in constrained conditions as well. I think that these sorts of data are kind of missing, as you said. And then like ultimately linking that with some kind of remote sensing. I think that the future is that we even at the moment we can't go on all the volcanoes to do these sorts of measurements, and so at some point we'll have to rely on satellites and other imagery to try to understand. So understanding the surface, the manifestation on the surface, and with what's going on at depth, I think is an important leap that we'll need to do at some point, to go from having to go there to you have to stand there to do the measurements, and to do it from a distance where it's safe.
But there are also some electromagnetic with drones and that are developing. I'm not sure that the chargeability is a parameter they can measure right now, but it's in development, so that's very cool for this. Yeah.
Yeah, it's all exciting. If were you at EGU last month?
No, I couldn't. No.
Okay, maybe I have some 3D images of the hydrothermal system in the dome
Good.
on my computer that you could have a look at.
I would like
if you're
to see.
interested. Yeah.
Time. So any further questions? I can do my questions during lunch.
We don't get a break during lunch.
Pablo too. So
There's a lot of notes on Pablo's paper.
So yeah, they're coming for lunch. So thank you so much, you guys, for the talk.
Thanks
I think
so
it was
much.
very interesting. It
Thanks
was
so
a pleasure to have you here. And Mike and Alexander, they are both working with us in the national project, the HydroCal, in Antarctic with Antarctic samples. So they are altered, not a lot. She's partially, maybe in the future. So we are looking forward to the results too. So these are pretty altered rocks. So if there are no questions, so thank you all for coming. Thank you guys for the talk.
Thanks.
And
for
thank
having
you for the listeners online. And we are going to shut down the connection
you.
right now. Thanks.